welcome to the first part of the Flink training. In this session, we're gonna give you a brief overview of Flink. So some of that might actually be kind of like overlap with the things you've seen in the keynote. And the second part is basically to get you started with the setup that you can use for all the other training. So you won't learn a lot in this session here. It's basically meant to prepare your hardware, your setup, that you can easily jump into the other training. So we didn't want to give an setup intro for all the other sessions, training sessions. So this is basically meant to set up your machine that you can participate in the other trainings without having to deal with setting up your environment. Okay, on the USB drives, on the USB sticks that I here on each table, you'll find a virtual machine image. As we announced, we prepared a virtual machine image. This is for VirtualBox, but it's also like an OVA file, which should be compatible with other systems such as VMware. So you can either use that one or you follow the steps to set up the Flink environment natively on your machine. All the other data, all the other files which are on the drives, you don't need to copy that. You can get basically everything also from the internet. If the connection is stable, we just put everything on the sticks to make sure we have a plan B if the Wi-Fi connection drops here. We have more sticks, yes. We gotta just put one on each table, but and please return the sticks, right? So we need them for the other sessions as well. Okay, so now I'm going to do the system overview of Apache Flink for those who have already touched Apache Flink or used it a bit. This might sound very familiar. For everybody else who hasn't been in touch with Flink or haven't looked at it in detail, you might find some interesting things here. Okay, Apache Flink, as you probably know, is first of all is a stream processor, which can be used for very different kinds of applications. And everything is executed on the same execution backend on this streaming data flow runtime. Flink has made quite a journey. As Costa said in the keynote, our Flink community is growing, and you all know we're an Apache project, which means Apache Flink is basically maintained and developed by an open community. Everybody is welcome to join the community. Everybody can participate. This is the whole project is under the government of the Apache Software Foundation. So if you're looking for an opportunity to contribute, you can talk to any committers which have this special committer tag here on the badges. So just talk to them if you wanna get in touch with the community and help to develop the future of Flink. Okay, what is Apache Flink? As we said before, it's basically has this core runtime for stream data processing, and on top of Apache Flink, there are two APIs, two basic APIs. First of all, the dataset API for batch processing, and the data stream API for data stream processing. And on each of these two APIs, there are more building blocks on top, or more domain-specific APIs or libraries, such as we have a connector for Hadoop MapReduce programs. We have a table API for relational data processing, or Jelly for operating on graphs, analyzing graphs. There's going to be a Jelly training as well tomorrow afternoon. We also have some machine learning here, and the green parts are basically all core Flink components, and the next to them the gray components are more like how we integrate with external systems. For example, with Google Data Flow, MRQL is another Apache project, which gives a high-level programming language that can compile to execute on Flink as a backend. And there's also a cascading. Oh, this work in progress should be removed. Cascading on Flink has been released already, so you can execute cascading workflows also on Flink. On the data stream side, we also have this table API, Samoa, which is an Apache project for data mining and machine learning on data streams, and also the data flow, Google Data Flow. All of this can be executed on different in different environments. You can run it locally on your machine. You can run it remote in a cluster. You can run it on Apache Yarn, using Tez, or in an embedded mode, which basically just allows you to run a Flink program on Java collections in your regular Java process if you want to. We support, or Flink supports, very different workflows and very different workloads in a native way. And these are, for example, like streaming data processing, heavy batch jobs. We do analytics on graphs, and also machine learning. And the question is, what does it really mean that all of these applications are, we operate on these applications natively? I give you a few context examples. For example, if we look into how systems deal with iterations, which are very frequently used for in machine learning applications or for operating graphs, a non-native implementation of going over iterations would be to basically do one iteration step, persist the data somehow in memory or on disk, do the next step, persist it in memory again. So it's basically just caching, applying one step over and over again. Whereas Flink is doing that a little bit different. In Flink, the data is actually flown. It's not materialized in the between steps. Looking at non-native support for streaming, this could be like discretizing the batch, as we heard in the keynote. A stream is an endless flow of data, and you somehow need to put it into buckets, into windows to operate on them. A non-native integration would be like to have an external stream discretizer, which just chunks the stream into parts, often referred to as mini batches, and then operate on these mini batches with one job at a time. And Flink is able to support all of these things natively because it has this pipelining streaming backend, which lets you, or which allows to send the data continuously through the system. Okay, so the Flink engine has a few nice features. As I said before, it executes everything as streams. You can operate in let the data even cycle around in your operator topology. So feed data back to a previous operator, and the data is flowing in circles. There's no persisting of data sets in memory. Flink deals with mutable state. So if you have a streaming program, you can basically have stateful operators update your state, and Flink will take care that this state is kept consistent. So you don't need to worry what happens if one of my nodes, one of my compute nodes disappears. Will my state somehow be lost? Flink will take care that this state is materialized and be put into another worker machine, and all of this happens in a way that the data or the state is kept consistent. Flink operates on managed memory, so Flink has its own memory management, putting data into serializing data into byte arrays in a serialized way, so that makes the configuration of the system much easier. So you don't have to fine-tune your parameters to avoid out of memory errors, and it also lowers the garbage collection pressure, so you won't see a high garbage spikes from garbage collection. So the whole application runs much smoother. And the engine has, as Stefan said, basically two code paths for batch and stream programs. So how does a Flink program look like? Flink programs are basically either these implement against the dataset API or the data stream API. And both APIs are, in fact, very similar. So they follow similar concepts. They follow, they actually even share a lot of code. And the basic abstraction here is that you have a data source. The data source produces in the either a data stream or a data set, depending on which API you're in. And then you apply some operations on this data set or data stream. These operations will produce another data set or data stream. And when you're done with your operation, so after an operation, you can do another operation, another operation, another operation. And once you're done, you can emit the data through a data sink, which can be a data file, or you can feed it back into Apache Kafka as a persistent log, write it into a database or whatever. So what could we, for example, do? So in the dataset API, it could look like this. So we read some certain information in here. It's funny triangles with the data somehow describes triangles. So then we apply a map function on that, make all of these triangles, convert them into one by one into a square. Then we do a reduce step to get multiple of these squares together, and in the end we emit the result. The data stream API looks quite similar. So we have somehow a stock feed which events from the stock, and then we can apply operations such as an alert, which is somehow a filter, which alerts if some stock value goes over a certain threshold value, or we can apply an aggregation on this data stream as well, usually within a window. So how are these concepts of streaming and batch somehow comparing with respect to input? The streaming input is, of course, infinite. The batch input is finite. The data transfer in the streaming case is, of course, pipelined. You always need to push the data from one operator to the other. You can't do like a batch exchange here. The data needs to be in motion. For batch, you can do either pipelined shipping, so you can either push the data further, or you can also do like a blocked connection, a blocking connection, collecting first all the results that an operator produces and then send everything in a batch. So there are some cases where you actually need blocking data exchange for batch cases. So in some cases you can either then run, you might run in a distributed deadlock if you only use pipelining, but Flink detects these cases and will automatically put a blocking connection there. And in terms of latency, basically latency in the meaning of how long does it take to see the first result. In streaming, this is the latency is of course low because you try to minimize the latency, and when I put something into my data flow program, I want to see a result as early as possible. Whereas in the batch case, when you do a full sort of all the data, the latency might be much higher. Flink is a parallel system, which means that it needs to be able to scale out. So if you write your program in the upper way, Flink's API will basically allow you to scale out this program, so it can be executed in many threads, and very often you can use like arbitrary scale out to scale it out from one node to 10, 100, 1,000 nodes. But scaling also has another meaning, which is like scaling up. So you can also build quite complex applications with Flink. So where each of these, it's kind of like a blurry image, but each of these small boxes here is kind of like one operator, and you can plug very, very complex programs together. In terms of data sources, Flink is able to read from quite a few different types of sources. The top one here mentioned is this collection-based, which is basically used for developing You just have regular Java collections that you can use to feed data into a program. This is very, very neat and very if you want to debug a program, or if you want to develop a program, because you don't need to attach it to a real data source. If you just want to check the application logic, you just put in a collection with some data, and then use that to use this data. You can also, of course, read from files or read from sockets, from Kafka, from database systems. So Apache Flink has, similar to Hadoop, this concept of input formats, which is very generic. So you can basically implement a input format for whatever source you have. Very similar for things. You can write data to regular files. You can print it to your console if you want to debug stuff. You can push it out to sockets, to Kafka, to databases, to Elasticsearch. We just, with a Flink 010, we're going to have like a rolling file output. This is actually meant for data streams. We have files which are constantly created, and more and more files are being created. And for whenever like the time you go into the next hour, you've got to create a new file. And this is done in a very consistent way. Flink comes with Hadoop integration, which basically means you can, of course, access data which is stored in HDFS. We run on Yarn. Basically, we actually run on Yarn in two modes. You can either spin up a Flink cluster on Yarn and keep it running there and just shoot your jobs there, or you can send out a detached job, basically just to run one Flink job on Yarn, which spins up the cluster, does the processing, and kills the Flink cluster after the job has been finished. You can also reuse Hadoop input formats and output formats. So if you have a very special input format for your data source, you can just plug it into Flink. So how does a Flink execute a Flink program? The general architecture should look familiar to most of you. So it's just a basic master client worker pattern here. We have a client which submits a job to the job manager, which is in Flink terminology the master. And then we have a lot of workers here, which we call task managers. And the client sends the program to the job manager, and the job manager then coordinates the execution here. The client basically takes the program, converts it into something which can be executed by the job manager. For the dataset API, this also involves invoking the optimizer, optimizing the program that was given to the client. It will then construct a so-called job graph, which is basically the program, or the representation of the program for execution. And then this job graph is given to the job manager, to the worker, which executes the program, and then the client will also retrieve the results of the computation. So basically, if the job was successfully executed, all the stats that were gathered during execution, and so on. The job manager, when it receives the job graph, has to take this job graph and convert it into a representation which is responsible for parallel execution. So it basically creates from the job graph the so-called execution graph, which is similar to a parallel version of the job graph. So all nodes are like scaled out. And then from this task, from this execution graph, there are these basically also define which tasks have been executed to process this job, and then the job manager assigns these tasks to the task managers and supervises how the task managers execute these tasks, and how the overall job is basically executed by looking what tasks need to be executed within the execution graph, and seeing what is currently running, what has been finished, what needs to be done next. Yeah, and the task manager receives these tasks to execute from the job manager, and executes them on its resources. The task managers are internally split out into so-called processing slots. So this is kind of similar to what you're, if you're familiar with MapReduce, Apache, Hadoop MapReduce. MapReduce also has this concept of map slots and reduce slots. In Flink, we only have one kind of slot, so you don't need to worry how to configure these. And these slots are basically then occupied by tasks to be executed. So as we said before, Flink can run on different kinds of runtimes. We're going to do in the training here, we're going to just do the local setup to basically, which is the usual setup for implementing programs, local debugging, local testing. But the good news is, once you've written a program in one, it can be executed actually on all of these different in all of these different environments. So the program doesn't need to be adapted, whether it's a local program or executed in a cluster. For the local execution, Flink starts a job manager or is running in a single JVM. So within this single JVM, it basically starts the job manager and can also start as many task managers as you configure. So everything runs in a single JVM process, and it just behaves like a regular cluster. So the job manager communicates with the task manager as if they were on different machines. So this is of course very helpful for debugging, because you kind of like get a very similar setup as in a distributed setting without having to actually set up a distributed system. The embedded execution, as I said before, is basically a very lightweight way of executing Flink programs. This is not meant for processing huge amounts of data. This is just if I have my one program and I want to execute in a very lightweight fashion on small data. So you shouldn't do that on huge amounts of data, because everything runs on Java collections. So this is not going through Flink's managed memory or whatsoever. This is basically just a completely different code path for the execution. When we do the remote execution, the client basically submits the job to the job manager. Here you see it's not in a single JVM, but here it's in a cluster. Each task manager now runs in a single JVM. So the client submits the job from remote to the job manager, and then monitors the status of the job. Basically sees if it's running, if it's finished, if it was successfully executed, or if it died somehow. The yarn execution is a little bit different. Here we use just a yarn cluster, and we have, as I said before, we have two different ways of executing jobs, either in this multi-user scenario where we spin up a cluster, let it run, and everybody can send jobs to this yarn cluster running on yarn, or you send out a single job, which brings up the cluster, executes, and then shuts the cluster down after it has been done. There's also support for executing Flink on TAS. This is a feature which hasn't been used a lot yet, but it basically uses Apache TAS runtime for all the data exchange and basically for scheduling and data exchange. Okay, now. We'll do a short comparison to other projects here. There are a few projects out there which are by Apache in the big data space. There is Hadoop, which is a batch-only system. There is also Store, which is a streaming-only system, and there are two representatives of the hybrid, which can do both stream and batch processing, which are Spark and Flink. And if we now, I won't go through all the details here in the table, so because it's quite a, I think it's not so interesting to just read them cell by cell. But overall, you basically see this basically compares the different batch alternatives. here from an API point of view, whoever used Apache Hadoop knows the API of ViewMap is rather low level, whereas Spark and Flink come with high level APIs which provide you with operations such as joins. Just highlight a few things like the memory management. Apache Flink is very disk-based, so it writes a lot of data is written to disk. Spark put a lot of memory. One of Spark's big advantages is to not writing so much to disk, but keeping the data in memory. But they're doing that in a way that they put a lot of the data on the JVM heap as objects, whereas Flink has an active memory management. And then there are different, more other things where these different systems differ. Looking at the streaming comparison, there's of course Storm, there's also Spark and Flink. How they treat streaming, Storm is like a true stream processor, which means it processes events by events. Spark is using mini batches for collecting data and then running full batch jobs on these mini batches. And Flink is also doing the true streaming here. I think we've seen most of that actually in the keynote already, talking about Flink's exactly one semantics, the flexible windowing, the latency and throughput characteristics of Flinks. Okay, so much for the introduction. Now you should get your hands on your laptops, on your machines, and we're going to try to set up Flink on your machines. There are also more people here to help me, so I think it would be a tough job to help all of you at the same time. But this bunch of people over there sitting on the couch and relaxing, they're also meant to work a little bit here and help you with the setup. There is we put basically all the training material on a website that how does it work now? Can't show anymore. Wait. So the website is dataartisans.github.io/flink-training. Let me see if I can get. I don't see anything on my screen here. Let's maybe you can do it like this. So this should be the URL. Is that working? Is it the correct one? Anybody tried? Yeah? Okay. You basically find everything there on this on this URL. If you click on the lessons menu tab, and then there is the system setup, which should be like lesson 2 or so. And if you then click on the hands-on thing, then you'll find the instructions for how to set up Flink on your local machine. If you just want to use the virtual machine, it's on the sticks. Copy it, copy the OVA file, import it into your VirtualBox or VMware, and just see if it's running, if it's working. You're basically all set up for the next sessions. If you want to install Flink on your local machine, we're going to help you with that if you have any questions. So the instructions basically tell you how to set it up on your local machine. If you want to use the virtual machine, just copy it, try it out. And if there are any problems, raise your hand. We're here to help you. Okay.